Hello and welcome back in this third and last episode of the second part of our series on how to build a digital guitar pedal. This episode will be on delays, while the next episode, here's what we did, a fuzz, which is working pretty well for a default example of a library. We only modified a small thing, which is this. The normal cubic amplifier function of the default file, we actually added a parameter which is int strength, which will allow us to control the strength of the fuzz with the parameters, with the rotary encoders and buttons we will add in the new video. But for this video, let's just focus on adding a delay. So, how can we do this? You may be familiar with some programming languages like Python or Java, and you have arrays or vectors or lists, and you can normally add some values, push some values in those arrays, like a pushback or a push or add functions. We could actually do this in C++ as well, but in our case, this wouldn't be a good idea. With this first callback, we are actually doing some real-time work. We need to process this input buffer really quickly because we actually need to do this a couple hundred times a second. That's why we cannot allocate anything inside this buffer. And also, they are telling us here it's not a good idea anyway. So what we should do about that is allocate some static sized buffer beforehand, and we need to fix a size from this. But let's imagine we only want a delay of 1 second, which means that maximum we will store this amount of frames of sample, and in my case it is 44,000 floats because our samples are floats, which means we can do a buffer, an array of 44,000 cells. However, at some point we will reach the end, which means we need to go back to 0. And the way to do this is called a ring buffer or a circular buffer. I think this illustration will make it easier to understand. Let's imagine here we have a buffer with 16 cells. It could be 1 second for us. Let's imagine a 16 sample rate. And here we are currently writing this cell. It means that it's the current note we are playing right now, and here is what happened 5 cells ago. So let's say here is what we are playing right now, and here read is actually our delay. So our maximum delay is 16 sample. Let's call this 1 second. Right now we are writing this, and we are playing the sound which happened 5 samples ago. It would be exactly the same for us, except that we are using an array of 44,100 cells. So let's start by actually making a few variables. As I mentioned before, normally we would use what's called user data. It's a pointer which can accept any object, and normally if you want to take some data, for instance from your main, and insert it inside the callback, it's what you would use. The reason for that, if you remember, is that we are not calling first callback ourselves. It's a callback that is called by Portfolio for us when they have some new data from the audio interface. In our case, we may store fuzz strength or the time of the delay, or is the delay even enabled, and stuff like that. But to keep it pretty simple for people not used to C or C++ pointers especially, I will do what we normally wouldn't do, is to store everything in global variables. So we will create a few of those variables. But first, let's create some variable for our fuzz. Here we have the strength, which before was hard-coded in our code. We can already modify this now. And we have a fuzz enable, which when we will add the rotary encoders and the button, will permit us to disable the fuzz in one click, for instance. But we will use it not now. Now let's add some variable for the delay. our first variable will be the length of the buffer. In our case, as I said, we only will want to store 1 second of sample, which means that we cannot have a delay greater than 1000 milliseconds. Of course, you can change it if you want. We could write directly 44 or 100 here, but let's just use the definer because it's used elsewhere. Now let's create the buffer itself. This buffer will be an array, which would be the size of bufflen, of course, and this is now created. We now have an array of 44 100 value. Now the delay. How many milliseconds or how many samples in our case do we want our delay to be? So let's create delay samples because we are not referring to milliseconds, and to keep it clear we are actually referring to samples, and that will be, let's say for now we want it to be 0.2 seconds, so a quite short delay, and that would be in our case equal to the sample rate times 0.2, or the sample rate divided by 5, because this is the amount of sample in 1 second. Now let's create the same variable we created for our fuzz, which is it even unable or not? And last variable, let's just call it, it's a bit short, but let's call it now, and this now would actually be equal to this place, like the current place you are writing, which means that the place you are writing is now, and the place you are reading is actually equal to now minus delay sample, because then again delay sample is equal to how many sample in the past you want your delay to be, and now is equal to, well, now. Okay, now those variables are added. Let's just, well, use those. First things first, we need to store what's currently happening, because if we don't store it, of course we cannot use it. So our buffer is called buffer, and let's store what's happening now in our buffer. So if you do remember, I'm using a mono input because my my audio interface is only mono input, but if you have a stereo input, you should do something here. For example, you could use this. It could be like, for example, here we are storing the 2 mono channels in the buffer, but it's not what I want for myself. Okay, now it is stored, but we need also to increment the now. We cannot just do like this, because of course at some point it will go above 44,000, and we don't want that, of course. So what we should do is increment it, but then we will do a modulo of the buffer, a buffer length, because now when now is equal to 44,099, it will go to 44,100, and then because of the modulo, which is the rest of the division, it will go back to 0. So it's exactly what we want. Good. We stored what's happening in the buffer, but we are not using it, so it's not really useful. Let's create a new variable, which we will call past, which would be the ID of the sample in the past, in the buffer. So normally what we would have done would be this, because actually let's say now is equal to this, and our delay is let's say this, then the past would be 18,000, of course. But let's say now our now is this, so it will be in the past, and we cannot have a position which is this. It just would not make sense. So we need to put it above 0. We could do a condition, but it's not really, well, useful to do. So we will just add the buffer length to this and then do a modulo, because it will never then be under 0, this expression here, and now we can do the modulo on the rest. So now let's store the buffered thing from the past, which would be equal to buffer past, since it's our ID. Now, instead of doing this, because it's not super convenient, let's just do this, call it fuzz, and call a variable fuzzed, which would be the result of this. This way it's easier to use, and we can even use it here. And lastly, since we have stored what's happening now in the buffer, and since we are incrementing it, it's actually all working, and buffered is indeed what happened G delay sample in the past. So we can actually try it already and do this. And now if I compile, it's really, well, it's only 200 milliseconds, so let's put something like this, it will be a bit more obvious to hear. Perfect, it works. But as you can notice, it's only like a slapback or a single echo. Normally in a delay, we would want some feedback. What we can do to have this is, instead of storing only what's happening right now, we can store also the buffered, which is we store in the current position, which is the now, we store the current value, but also the value from the past, here 9. And now we try, and there is a small problem. Now it's infinite. It's like a delay with a feedback to the maximum. And of course we don't want that. So we need a way to make it lower each time. What we can do for that is, for instance, multiplying in the buffered, not storing exactly what happened in the past, but degrading it a bit. This way, when we use it here again, it will be a bit lower each time and each time. And it works as expected. But as you can notice, actually I just noticed, we are not storing the fuzz, we are storing the raw input. But we are outputting the fuzz, but we are not. This means that what we are hearing is the first one is fuzzed, and then the delay is only the raw version of it. So what we should do to fix this, of course, is store the fuzz value. Okay, it works like we want. We could tweak some parameters, let's say maybe put the feedback a tiny bit higher. Yeah, it's a mess, but at least it works. A thing that we could do also is parameterize this value, because in a normal delay pedal this is roughly equivalent to the feedback parameters, and of course we would like to change this in the same way that this parameter, which we wouldn't do like this, would be equivalent to the volume of the fuzz, and we will also want to parameterize it. But first, if you remember, you create two variables, delay enabled and fuzz enabled, and let's just use it. It's not the best way, but let's just use some ternary condition here, which basically means if fuzz is enabled, then in fuzz you store this, which is the fuzzed signal, and else, if it's not enabled, you just store the raw inputs. It's not the best way because here the condition will be executed each and every turn of the loop, which is not useful because this parameter won't change very often. So normally we should put this as a condition and outside of the loop. Same thing for the delay. We still do want to store this, because if you open the delay, if you enable the delay, you could want it to work immediately without having to wait for it to be stored. So it's a reasonable idea to store it all the time, but we still need to put the same condition here, delay enabled. So buffered value, if delay is enabled, then we take the value from the past, which we are diminishing a bit, and if it's not enabled, then we put 0. And same exact thing as fuzz. Ideally you should put that outside of the loop because it's not the best for performances. And now if we run it again, perfect, and if we run it again without those enabled, and now we just have our raw signal chain. So my guitar directly plugged to the Raspberry Pi, plugged to my recording audio interface. So it's working as we wanted to work, I guess. And the only thing we need to do now is actually plug some components like rotary encoders and buttons to our Raspberry Pi and get those inputs inside our C++ code and make it so we can modify in real time with our buttons and encoders those values. And this, we will be doing this in the next part of this series.